Hi, my name is Emma Doring, and this is my Physics 2 Lab 3 on circuits. The purpose of this lab was to use both the loop rule and the node rule to look at the behavior of circuits with resistors and capacitors in series and parallel, as well as measure currents and potential differences along circuits' paths. Some models and fundamental principles that I used were the loop rule, which comes from the conservation of energy and says that the total potential difference of a closed circuit is 0. This was used in the first circuit to ensure that the potential differences around the circuit added up to 0. Next is steady state, and that says that current flow is constant throughout a circuit if the net electric field is non-zero and constant. This is applied again in the first circuit. Then I used the natural log of the potential difference over the initial potential difference equals negative T over RC to find RC, which is the time constant. Next, I used the node rule, which comes from the conservation of charge and says the current coming into a node must equal the current coming out. This is verified with 2 ammeters in the first circuit. And lastly, Ohm's law, which says that the change in potential difference is equal to the current times the resistance. It's used to calculate the current in the first circuit. The preview of my results, so in the first circuit you can see the predicted versus actual current. The loop rule, which is just the sum of the voltages around the circuit, is 0, and then the resistances for each of the components of the circuit. Then for the second circuit, you can see the times it takes for the capacitor to charge and discharge, and then my time constants. For the first circuit, the system is the circuit and then the surroundings is nothing. In order to complete this part of the lab, I created a circuit with 2 1.5 volt batteries, 2 ammeters, and a 47 ohm resistor and 100 ohm resistor. I read the current from the ammeters, switching them around and exchanging one with a voltmeter. I measured the potential difference around the circuit, measured the current with an ammeter in parallel with one of the resistors, and then calculated the resistance of each component. For the results of this part of the lab, the predicted current was 0.0204 amperes, while the actual was 0.15. The current reading didn't change when the ammeter was backwards, and then when one ammeter was replaced with a voltmeter, the current was 0 and the voltage was -3 because the voltmeter has high resistance and causes the circuit to act open. The current is 0.02 amperes with only one ammeter. The total change in potential difference, of course, is 0 by the loop rule. The ammeter reading doesn't change when the voltmeter is attached because, again, the voltmeter is high resistance. And then when the ammeter is in parallel with the 100 ohm resistor, the current increases through the original ammeter. On the right, you can see the voltages around the circuit, and then on the bottom, the resistance of each component. For the next part of the lab, the system, again, is the circuit. The surroundings is nothing. First, I created a circuit with a 10 ohm bulb, a 9 volt battery, and a 0.2 F capacitor. I assessed the light in the bulb as the capacitor charged and discharged, measured the amount of time it took for it to charge and discharge, and then repeated the whole thing with a 20 ohm bulb. And then I created a circuit with a 30 ohm bulb, a 0.2 F capacitor, and a 9 volt battery, and measured the voltage of the capacitor. And then tracked 20 seconds of voltage data while it was discharging. Then I plotted this in a graph and found the time constant. For the results of this, so the light in the bulb starts out bright and it slowly turns off when the capacitor charges and discharges, and then the current in the circuit slowly diminishes again as it charges and discharges. With the 10 ohm bulb, it took 14.08 seconds for the capacitor to charge and 26.06 for it to discharge, and then for the 20 ohm bulb, it was 23.51 and 51.62. You can see my computed and predicted time constants at the bottom, and then also my graph. So comparing the models for the first circuit, the predicted and actual currents were pretty different, and then my predicted and actual time constants were also pretty different. Some possible sources of error: the timer could have been misaligned with the voltmeter when I was timing the voltages in the RC circuit, and then also circuit and components are all simulated, so this is not real data. The discussion questions: if I were doing this in real life and used an actual ammeter, it would have some resistance, which would decrease the current in the circuits. And then if I used a real battery to charge a real capacitor with no resistor, the RC value would be 0, so the ideal model would predict the capacitor to reach full charge immediately, but this would not happen because there's always going to be some resistance in real life.